Assalamualaikum and good morning. So welcome to week 6 of our video lecture. We are now in topic 3. So we begin topic 3 on DC circuit analysis technique, where we are going to look at a few theorem that we're going to use in order to analyze a more complex circuit with multiple mesh. We will begin with mesh analysis and nodal analysis today. So the objective of this topic number 3 on DC circuit analysis technique is, of course, to apply KCL and KVL. So basically, all of these theorem are application of KCL and KVL, but in a more complex network. So we are going to use what we call as today, specifically, we're going to look at these two, but overall in this topic, we're going to look at all these 4 points. Today, we're going to look at what is mesh analysis and nodal analysis. And then later on, in coming week, we're going to look in topic 3, we're going to look at, try to understand and apply Thevenin and Norton theorem. So it's a theorem basically to transform your circuit in order to facilitate the analysis. We also have, which is not written here, briefly we will explain about the theorem of superposition in analysis of circuit. In point number 3, we're going to look very briefly, quickly into a very specific configuration, which is a star and delta connection. So we have a load that is connected in star and delta form. This is especially true for basically for our three-phase circuits later. And then finally, we'll try to very quickly understand the condition of maximum power. How does a load work? That pulls power and therefore current from the supply. So for this topic, just like in previous topic, in topic number 2, basically what we are going to do is mostly demonstration through several examples. So let's begin. We will start with mesh analysis. So what is mesh analysis? Mesh analysis, to make it simple, is basically a method that we use to find currents. So it's a method that we use to find currents in each branches in a multiple loop mesh network. So by application of KVL. So what we're going to look at is basically when we have a circuit with multiple mesh or multiple loop like this one. So here we can see that there is 3 mesh, 1, 2, 3, and in terms of loop, of course, there are more loops. There are multiple loops that you can go through. But to be specific, in terms of mesh, the smallest form of loop, we have 1, 2, 3, right? So when we have multiple loop like this, and we want to find current inside each branches, inside each branches. So what is branches? Branches is basically a line where we have a loop. So for example, across this 20 ohm, across this 30 ohm, 40 ohm, these are branches. You have one branch over here, one branch, and another branch. So there are multiple branches. So if you want to find currents in those branches, in a circuit where it is constituted, it is made of multiple loops, we are going to use what we call the one of the easiest method is to use what we call as mesh analysis. So to summarize a bit, we'll go through an example. But to summarize, what do we have in the method? The first one is basically to assign current circulating inside loops. The first step is to assign current circulating inside loops. So basically, if we see there are 3 loops, we will assign a current with a certain direction. We say that there will be a current in this loop. There will be a current that's circulating in this loop and a current circulating in this loop. Because we know that in each loop there will be current circulating in that loop, right? And then after that, after having current circulating in that loop, what we're going to write next is write KVL in each loop. So let's say we're going to take this loop as a first loop. We're going to write the KVL. So we're going to sum up all the voltages, because once we have current, we may write, for example, the voltages across all these branches as the product of resistance and the current that we have assigned previously using Ohm law, right? So we're going to write KVL in these 3 loops. And then, knowing that we have 3 current and 3 loops, and we have 3 equations from KVL in those 3 loops, we can therefore solve an equation to find the currents in those loops, the currents of the loop. So current in a branch, later, once we found we write the KVL. Current in the branch is basically the sum of loop current. So if, for example, the branch over here, we have it is an interaction of 2 loops, the loop at the bottom over here and the loop at the top over here. So this the current in this branch is basically the sum of the current in this loop and the current in this loop. So we'll see how we write the KVL using that, and then try to solve it together. So in this example, we're going to treat this example. The example asks us to calculate the current in each branch of the network shown. So we have this network with 3 loops. We have 2 voltage supply and multiple resistors. They want us to calculate, the question asks us basically to find the current across each resistance. So let's begin. So the first thing, as we mentioned in the method just now, the first thing that we need to do is to calculate the current, to assign the current loop in each loop. So here what we do from the circuit that we have previously, we now have this circuit where I have assigned basically a certain direction of current in those 3 loops. So I'm calling this loop as loop 1, and I assign there is a current, we consider that there is a current that circulate in this loop following a clockwise direction. And then we call this loop over here as loop 2 with its current in clockwise direction. And then we consider that there is the loop number 3, we call it as loop number 3, where the current is circulating in this loop with a clockwise direction. And we call those current as in loop 1 as the current circulating in it as E1, I1, I2 for the current circulating in loop 2, and I3 as the current circulating in loop number 3. So what we do next is basically we can write the KVL in each loop. So let's have a look at the first loop. So if we write KVL, of course, what you need to do is, as you remember, you have to basically identify all the voltages that you have in the loop. So for example, in this loop, we have 3 voltages. So the EMF by the power supply of 100 volt, you have the voltage in the opposite direction of the current 1 produced by basically the resistor of 60 ohm, a voltage across the 30 ohm in opposite direction of current I1, and then a voltage of across this 50 ohm in the direction opposite of I1 as well. And then at the bottom of here, of course, we have also the voltage supply. We have 3 voltage supply, just now I said 2. So the third voltage supply that has 20 volt on it, right? So in the opposite direction of the 100 volt. So if we write the KVL, we see the 2 voltage supply 100 minus 20 equals to all the voltage inside the resistor. Why do we write it on the other side? Is because basically the voltage is opposing the direction of the voltage of the EMF. So we have the first one, basically the voltage created by the 60 ohm. So I1 multiplied by 60. The voltage created by 30 ohm, I1 multiplied by 30. The voltage created by 50 ohm, I1 multiplied by 50. Okay, what is this term at the behind here? So this term is basically when we look at the resistor of 30 ohm and 50 ohm over here, 30 ohm and 50 ohm, the current that goes into this, for example, for instance, let's take the 30 ohm. The current that goes into the 30 ohm is not only I1, because the branch of 30 ohm is basically the branch in between loop 1 and loop 3. So the current that goes into this 30 ohm is basically there are 2 currents. The first one is the current that is coming from I1, and then the second current is basically the current that is coming from I2. So the voltage inside the 30 ohm, there is the contribution of I1, which is I1 multiplied by 30 ohm, but also there is I3 multiplied by 30 ohm. So here you have I3 multiplied by 30 ohm. Why do we have the sign minus? It is because if we look at the direction of current, if we're writing for loop 1, so the direction of current is from left to the right in 30 ohm, but the current I3 from the point of view of 30 ohm of loop 1, it is basically, it goes in this direction from right to left. So the current is negative, that's why we have minus I3. So I3 is basically minus in the loop 1, minus I3 multiplied by 30 ohm. So the same goes for the 50 ohm. We have the voltage is created by I1 multiplied by 50, but also created by minus I2, because I2 goes in the opposite direction of I1, minus I2 multiplied by 50 ohm. So that's why we have minus I2 multiplied by 50 ohm. So that's how we write the KVL. You have to remember, when you write the voltage on a resistor that is in between the 2 loops, you have to include the current of the loop that you're writing in minus the current of the loop that is adjacent to it, right? So we have this KVL. So when you write, basically when you simplify everything, so you got AT equals to 140 I1 minus 50 I2 minus 30 I3. So the same goes for loop 2. So let's have a look at loop 2. In loop 2, the MF that we have, basically we have the MF of 20 volt plus 50 volt. So 50 plus 20 equals to, so the voltage across the resistor, we have the resistor of 50 ohm, 40 ohm, and 10 ohm. So the 50 ohm, the current is I2 minus I1. So that's why if you look at 50 ohm multiplied by I2 plus 50 ohm multiplied by minus I1. So that's where we get minus I1 50. And then for the 40 ohm, you have I2 multiplied by 40 minus I3 multiplied by 40. So I2 multiplied by 40 minus I3 multiplied by 40. And then for resistance of 10 ohm, in the resistor of 10 ohm, it is not adjacent to any other loops. It's only in interaction with current I2. Therefore, you have I2 multiplied by 10. So you have here I2 multiplied by 10. So that's where we get this equation over here. And you can do the same for loop 3. In loop 3, why do we have 0 over here? Because we don't have any EMF. So when you write your KVL following the direction of the current, you will not have anything. But in the opposite direction of the voltages, you have the voltage that come from the 30 ohm, 20 ohm, and 40 ohm. So again, for 30 ohm and 40 ohm, 30 ohm is multiplied by I3 minus I1. So 30 ohm multiplied by I3 minus 30 multiplied by I1. For 40 ohm is I3 multiplied by 40 minus I2 multiplied by 40. So I3 multiplied by 40 minus I2 multiplied by 40. And then we have, of course, the 20 ohm is alone, it's not in interaction with any other loops. So we have 20 ohm multiplied by I3. So there you go. You have 20 ohm multiplied by I3. There's no part over here. So when we reduce it, it will become this equation. So when we look after we have all the equation, what you have remarked, what you can observe is basically you have 3 equations with 3 unknowns. So the unknowns are basically the currents I1, I2, and I3. So in each equation you have I1, I2, I3, I1, I2, I3. We don't know what the value of the current is, but we have 3 equations. Therefore, you have learned solving a system of equations. We have 3 equations, 3 unknowns, so you can solve the equation to get I1, I2, and I3. So we continue. We have 3 equations just now. The 3 equations are over here. You need to solve it to find I1, I2, I3. What I strongly advise you to do is to put them in the form of matrix and solve the matrix. I think you know how to put them in the matrix form. You have learned this in basically a matriculation or A level in STPM. So from this form of equation, you put it in the form of matrix, because later you can enter your matrix into either your calculation program such as MATLAB or your calculator. So I think you know how to do it. So basically the first line is basically the line that comes from equation 1, right? So you have over here the voltage 80, 70, 0 equals to I multiplied by R. So this is all the resistor is a matrix of resistors. So if you look at this first line, it comes from all the resistor in first equation that multiplied by I1, I2, I3 equals to voltage in the first equation. So 80 equals to 140 multiplied by I1. So you can find 140 I1 minus 50 multiplied by I2 minus 50 I2 minus 30 multiplied by I3 minus 30 multiplied by I3. So from this, you transform it into matrix. So I really suggest you to do so to make it very clear when you try to solve it using a computer program or your calculator. So I'll let you solve it on your own. So when you solve it, you would find that I1 equals to 1.65 amps. So the current that's escalating as I1 is 1.65 amp. I2 is 2.16 amp and I3 equals to 1.5 amp. But we have not finished yet. Why? Because the current that we find is basically the current circulating in the loops. It's not the current across each branch. Okay? Because the question just now, if you look at the question asks us to calculate the current in each branch. So for example, this is the current. What they want is basically the current, for example, across 30 ohm. The current across 30 ohm is not I1, it's not I2, it's not I3. It's the interaction between I1 and I3. So let's see how do we do it. So as I mentioned just now, current, for example, let's have a look at all the resistors. We'll take, for example, a few resistances first. So for example, for the 60 ohm. So where is the 60 ohm? 60 ohm is over here. So what is the current that goes through 60 ohms? If we look in comparison to I1 that we calculated just now, the current that goes through 60 ohm is just I1 because it's not interaction with any other loop. So I1 is I across 60 ohm is I1, therefore equals to 1.65 amps. But now for 30 ohm from the point of view in direction of I1, it is basically the interaction between I1 minus I3. Therefore, you have to take I1 minus I3. That gives you 1.65 minus 1.5. You get 0.15 amps. So the same goes for the others. I'll let you try to do it on your own and find the answer that's given over here. You should to answer this question, you should calculate all the current that goes through each resistors. So that is a mesh analysis. So if we were to recap, the method is basically from the question just now, the network. What you need to do is to assign the direction of current, assign current in each loop, I1, I2, I3, and then you write the KVL in each loop. And do not forget the voltages across the resistor that is adjacent, that is in contact with two loops. You need to take into account the current of the two loop. For example, for the 30 ohm, is basically from the point of view of loop 1. When you write KVL in 1, it is I1 multiplied by 30 ohm minus I3 multiplied by 30 ohm, right? And then after writing KVL, you can write your system of equation and then finally solve the system of equation. Okay. So the question that you might ask, what happened, for example, if is it necessary to assign the direction of current following clockwise? No. The answer is no. You can basically attribute any direction, assign any direction you wish, and it can even be non-uniform. For example, if you want to do in loop 1 clockwise but in loop 2 counterclockwise, you can do that as well. But of course, what's going to change later is the sign in your equation, and you will fall back into the same answer at the end. Just make sure that you follow the direction that you have assigned. But to standardize and to make it easier for you to not become confused, I strongly suggest for you to always select the same direction of current, for example, clockwise direction, so that you're not going to be confused. Okay, so that is mesh analysis. To check your understanding, I strongly suggest you to do this exercise. So this is an exercise that we're going to try to do together as well in tutorial session, and we'll try to simulate it using a multi-sim to familiarize you with instrumentation and measurement on electrical circuit. So what we have here is basically the answer. The question asks us to calculate the value of current inside the 8 ohm resistor. So 8 ohm resistor is over here. Here we have a circuit with 3 loops, and we have 2 voltage supply and a few multiple resistors that is either on only a branch that is not in contact with other loops, or in the branch that is in contact with multiple loops like the 15 ohm and 8 ohm. So using the same method that we had just now, please try to solve this. This exercise. Next, we are going to look at the second method. So the second method here is what we call as nodal analysis. So what is nodal analysis? In brief, nodal analysis is used to find the voltages on a node junction of a circuit using KCL. So for example, let's take a look at this circuit. So this is a circuit basically that has a multiple loop. Therefore, it has a junction. It has multiple junction or node. The term nodes and junction are the same basically. If we want to find what we call as voltage on a node, so voltage on a point, we need to use this nodal analysis. So nodal analysis basically use KCL because we are talking about node, right? But there is a remark here. What do we mean by voltage on a node? Because previously, when we talk about voltage usually is when we observe the potential difference between 2 points, right? So 2 points mean, for example, the voltage across 30 ohm is the voltage comparison of voltage at this point, node 1 and node 2. So voltage across 30 ohm is basically when we compare the voltage, it is across 2 points between node 1 and node 2. But what we call as node voltage or voltage on a point, it is basically the voltage between this point, the node that we mentioned, in comparison to a ground or to a reference node. So for example, in this circuit, we have a reference node over here, a ground. So the voltage of node 1 is basically the voltage, if I may draw, is a voltage between this node 1 and the ground. So this is V node 1, and V node 2 is basically the voltage from the point V2 node 2 to the ground. So this is V node 2. Okay, so it's not a voltage across only one component, it's a voltage between that point and a reference ground. So it may include between it several component, or probably in this case only one component, right, on one resistor, 5 ohm or 7 ohm in the case of V1 or V2. Okay, so what is the method? So the method here is basically the first thing. Usually what we will have is this circuit without any ground. You may be given with a ground or you may not be given with ground. What we need to do first is to choose a reference ground. So we need to attribute or assign a ground to the circuit. So usually the usual practice is basically the ground is usually attached to the negative terminal of a supply. So for example, here we have a current supply that push 1 amps outside of the current supply. So here is basically the negative terminal of the current supply. So usually we put at the negative terminal the grounding or the reference node. Okay, and then after doing that, what we do is we have to assign currents in each branch connected to the nodes. Okay, so so here after choosing the ground, label the other unknown node. This step first. So the other unknown node, for example, here what interests us is node 1 and node 2. And then from that node, we have to, number 2, assign currents. So in each node, we have to assign the current. So for example, node 1 over here, we can see there are 3 currents that interact with this node. The current from this branch that coming from power supply, the current that is connected to the resistor 5 ohm, and the current that connected to resistor 3 ohm. In node 2, there is 2 current that is connected to 3 ohm and current that connected to 7 ohm. And one remark, the current that is connected to node 1 from the resistor and the current that is connected to node 2 from the resistor is basically the same current. So the current that can interact node 1 and node 2 over here is basically the same current, which is the current that goes through the resistor of 3 ohm. And then after you have assigned the current, we'll see later in the example, what you do is basically you apply KCL on the node. So for example, node 1, you have assigned the current. So you calculate, you write the equation of KCL here. The same goes for here, you write the KCL. So then what will happen is that you will have 2 equations and hopefully you have 2 unknowns, so you can solve the resulting equation that you found from your KCL. So let's have a look at this example. We'll try to do that, learn that by demonstrating an example over here. So the example over here asks us basically to calculate the voltages V1 and V2 in the circuit shown. So V1 and V2 is basically the voltage on node 1 and voltage on node number 2. Okay, so we'll do step by step. So the first step, as we mentioned just now, is basically to attribute or assign a ground. We have a reference ground. So the voltage that we are calculating over here, V1, is voltage from V1 to the reference node. It is also voltage across the 5 ohm. Therefore, voltage number 2 is voltage from node 2 to the ground. So it's also the voltage across the 7 ohm. Okay, right? So we have now the ground, and then we call the other node, this node as node 1 at point V1, at the voltage V1, this node as node 2. What we do next is, in step number 2, is to attribute or assign the current in each branch that is interacting with the node that we have identified. So for example, in node 1, what current do we have? We have 3 currents, and in node 2 we have 2 currents. So what are the currents? You have to identify them. So the current that goes through the 5 ohm, we don't know what the value is. The current that goes from the power supply, we know it is 1 amps. The current that goes to the 5 ohm, we don't know what it is, but we know the value will be V1 divided by the resistor 5, which is basically the ohm law, right? V divided by R. And the current that goes through the 3 ohm, what is it? It is basically the voltage between point 1 and point 2. Therefore, the voltage is basically V1 minus V2. If I can draw the voltage, so basically it is this voltage, it's V1 minus V2, or we call it as V12. We may call it as V12. So the different potential between 0.1 and 0.2, this is the voltage across 3 ohm, divided by the resistor 3 ohm will become the current. So this is the current over here. And then we have also the current in node 2, this branch. So what is the current? We don't know what the value is, but we know it will become V2 divided by the resistor 7 ohm, right? Okay, so now if we look at these currents, you may have to assign as well the direction of the currents. So you can assign the proper way of assigning the current is, of course, when you have current that's coming from the power supply, the current will go from the power supply into the node, and then it will be divided into the branch. So one will go in the direction of 5 ohm, another one will go into the direction of 3 ohm, and then the current continues to 7 ohm. So that's why we have this direction that we have assigned over here. Now, completing step 2, we have the direction and we have the value of the current, potential value of the current, because we don't know yet the value. Here we have 1 amp, of course, but here it's V1 over 5. Here is V1 minus V2 over 3, and here is V2 over 7. So step number 3 is to apply KCL and write your KCL on node 1 and node 2. So let's have a look at node 1. If you look at node 1, we have 1 entering current and 2 current leaving the node. So we would say that entering current equals to leaving current. So 1 amps will be equals to V1 over 5 plus V1 minus V2 over 3. So that's what we have over here. So 1 amp equals to V1 over 5 plus V1 minus V2 over 3. So that's the KCL from node 1. If you have to simplify, so when you simplify it, you will have V1 multiplied by 1 over 5 plus 1 over 3, because you have 2 V1 over here, minus V2 over V3 equals to 1. So now you have V1 and V2 in this equation. Let's have a look at node 2. Hopefully we have V1 and V2 as well. So in node 2, the current is entering current V1 minus V2 divided by 3 equals to leaving current V2 over V2 over 7. So V1 minus V2 over 3 equals to V2 over 7. So we have this current over here, this KCL over here, the relation between the current entering current and leaving current. So if we have to simplify, we have 2V2 over here. So if we bring the V2 on the other side, so what will happen is that we have V1 over 3 minus V2 multiplied by 1 over 3 plus 1 over 7 equals to 0. So we now observe that we have two equations and two unknowns, which is V1 and V2. We have V1 and V2 in equation 1, V1 and V2 in equation from node 2. So you can proceed to solving your system of equation. Continuation of what we are discussing. So what you need to do, just solving the equation. So you can use your preferred methods of solving equation. You can put so this is just two unknowns, so you can simplify each other. If you have more nodes, more KCL, for example, just like in mesh analysis just now, you have 3, then I strongly suggest for you to write basically the matrix to solve the equations. But in this case, it's pretty easy. So if you solve the equation, I basically will let you try to do it on your own. It's just simple solving equations. So you would find that V1 equals to 10 over 3 volts and V2 equals to 7 over 3 volts. So that is nodal analysis. So if you have to recap from the circuit, if you want to find a voltage, so nodal analysis basically when they ask you to find a voltage on a node, right? So here voltage in node 1 and voltage in node 2 were asked by the question. So what we need to do, as I mentioned just now, the first step is to have a ground, so that you know the V1 is basically the voltage between this point and this ground, V2 is this point in this ground. And next, what you need to do is to assign the direction of current and know the equation of the current. So for example, here we have I1 entering, 2 current leaving. The current leaving is current leaving over 5 ohm is V1 over 5, because it's the only resistor in this direction. And here the current over here, so is the voltage across this resistor divided by 3 ohm, and the voltage across the resistor is basically V1 minus V2, right, divided by 3, and over here is V2 divided by 7. And then after assigning the direction and identifying all the current, you write your KCL. So once we write a KCL, we end up with this, and then finally you will observe that you have two equations, two KCL with two unknowns. So you solve it using resolution of a system of equation, and you'll find the answer. So you may have more or less complex system to solve, but the method is always the same. Just to pay attention or to be careful when you write the voltage. For example, you write the current. So the current over here inside this resistor of 3 ohm is V1 minus V2 divided by 3 ohm. And here is V1 divided only by 5 ohm. Here is V2 divided by 7 ohm. So you might have multiple components. So you have to be careful with your ohm law. So what is the voltage and what is the resistor that is included to calculate the current. Again, like in mesh analysis, to test your understanding, I'll suggest for you to do this exercise. So you have a bit more complex circuit. You are given with a reference node already. You have 3 loops in this circuit. We would like to find the node voltage of V1 and V2. So using a node voltage or nodal analysis method, calculate the voltage at node V1 and V2. So again, what we mean by node voltage V1 and V2 is the voltage between V1 and the reference, V2 and the reference. So please try to do this. To do this, we will also try to do this together during tutorial, just like the mesh analysis question, and we will try to demonstrate the answer using a multi-sim. So basically a simulation that will help you in basically getting familiarized with analysis of circuit in laboratory. So it is a simulated, it is a virtual lab, but nonetheless, it will get you familiarized with the component and with measurement of voltages, currents, and using, for example, instrument like multimeter and oscilloscope. Multimeter especially in this case. Okay, so that's all. Thank you very much, and I'll see you during the tutorial, and I'll see you next week as well for the next topic, next section in the topic 3, theorem and analysis technique in DC circuit. Thank you very much.